This video is on the conservation of momentum. And the first thing that I would like to bring to your attention is playing a game of billiards. So you're playing pool, right? So you're going to line up all the balls, you're going to take the cue ball, you're going to strike the cue ball with your stick, and it's going to hopefully collide with the other balls, and thus they will now be in motion. So something that was in rest is now in motion. How? Yeah, something struck it. Okay, so that's elementary, but now we're going to talk about the physics of it. So what is actually occurring in this to make one ball stop moving and one ball begin to move? And ironically enough, or coincidental, I guess is the right word, not ironic, they are moving at the same velocity as the one that is now at rest. So it was literally a transfer of energy. That's not this unit. That will be on work, energy, and power. This is more so just going to be on your momentum, impulses, and collisions. So now we're talking about the collisions since we have a grip on momentum and impulse. Okay, so right now at this point when you're going to break at the beginning, ball A was moving, so it has a velocity, so it has momentum. So velocity equals some value, therefore it has some momentum, right? Momentum's not equal to 0. If your velocity was 0, P equals mv, so P equals m times 0, obviously P would equal 0 then regardless of what the mass of the billiard balls were. Agreed? Okay, fabulous. With that in mind then, what is the momentum of billiard ball B, guys? That red one there. It's just chilling out, right? So what is its velocity? Its velocity is 0. Well, P equals m times v. Since your velocity is 0, then your momentum is also going to be 0. The object is i.e. at rest. Okay, so momentum of ball B, P equals 0 kilograms times meters per second because velocity equals 0 meters per second. Therefore, object is at rest. Make sense? Yeah, okay, so cool. They collide. What happens? There's a collision. This collision happens from between the two balls. So when A hits B, the momentum is transferred to B. Thus, there is a conservation. Because what happens to A at that point, guys? If they were struck perfectly, granted we got some different factors here, but in an ideal situation, the momentum of A would literally be transferred to B. So there would be a conservation of momentum that would be achieved. So I'm just going to kind of bracket these guys together and just say conservation of momentum. And this is because okay, next one, the after effect. If it is complete transfer of momentum or conservation of momentum, then you would say that the momentum of ball A is now whatever B's was. And B was at rest. So the momentum of ball A, momentum is going to equal 0. Agreed? This is because the velocity equals 0 meters per second because ball A is now at rest. Okay, what about the momentum of ball B? The momentum of ball B is now whatever the momentum of ball A was. So, whatever ball A's momentum was is now P of ball B. This is because momentum was transferred. I.e. conservation of momentum. Simple, right? Straightforward. Very, very, very straightforward on this analogy and philosophy here. Okay, so check out the equation. M times V equals P, right? So you have your mass times your velocity equals your momentum. That's where they came up with this number, right? Okay, so check this out. this ball was not 100% at rest, right? That's exactly what that's saying. So the ball had a little bit of movement on it. Don't really know why. But according to this table, the momentum in that collision that you just saw between the white and the red billiard balls shows that one was not completely at rest. But check this out now. If one of the billiard balls was completely at rest, then your momentum would be 0. And then your momentum is literally transferred over, right? Ball A is now ball B's momentum. Making sense? Okay, so there is literally a transfer of momentum, i.e. conservation of momentum. Some of it is lost as heat, light, and sound. Those are your non-mechanical energies. We're not there yet. That would be work, energy, and power. But heat, light, and sound give you a, what words do I want to use? A lack of complete transfer of, i.e. energy. But in this scenario, we're talking about momentum. Right, because you can hear those billiard balls colliding. There is some heat that is generated, i.e. given off from the felt on the billiard ball table or from the two objects colliding with each other. Okay, so the relationship between the variables. The equation I want you to hone in on is P equals mv. In the equation P equals mv, when m is constant, how are V and P related to each other? V and P. V and P are directly related to each other. Yes, it would be a direct relationship. Okay, when B is constant, how are P and M related to each other? P and M. Good, guys. They're both directly related to each other. So we can see a lot of direct relationships here. Let's switch it up a little bit. When P is constant, how are M and V related to each other? M and V would be indirectly related to each other. So once again, using this equation, think about the relationship between your variables. Once again, keeping in mind that something has to stay constant. Okay, so the equation for the conservation of momentum. Technically, the general equation, like the real original equation would be delta PI equals delta PF. Well, the problem most likely, guys, is not going to come out and say the initial momentum is this. It's going to say an initial velocity of, a final velocity of, an initial mass of, a final mass of. Although technically, like, things don't tend to lose mass as they're moving, right? Like, pieces aren't falling off your car as you're moving down the highway. You're not losing body parts as you're walking through the hallways. I mean, yeah, so usually you can bank on your mass being given to you and that not changing unless it's like saying like a pickup truck initially at this mass stops and picks up a load of topsoil and now it's at that mass. That kind of a thing, but it's usually you're not going to be losing mass. Okay, so anyways, delta PI. So that would be MVI, and then delta PF would be MVF. Okay, but you have two different objects, right? So really what we're going to look at here is going to be your MVI, like M total VI, equals your M total VF. So the real breakdown, you can skip this. But this is the original equation. Okay, that's the one that you want to use, but you can skip the M total VI, blah. Okay, so break this down to right here. This is what I should see as like the second line in your work. So this would be M1V1I plus M2V2I equals M1V1F plus M2V2F. Make sense? Okay, so this is totally cool, guys. What if it says an object initially at rest? An object initially at rest. You can hack off M1V1I. If it says both objects are at rest, then you're going to hack off M1V1I and M2V2I, right? What if it says an object comes to rest or an object stops? Then you're going to hack off some of that stuff. So this is going to be like crazy simple. You just have to pay attention to the way that the problem is worded. Make sure that you understand the difference between the first object and the second object. So we're going to talk about two objects and the way that they collide with each other. So billiard ball 1, which was the white ball, is M1V1I. Billiard ball 2, which was the red ball, would be like M2V2I. Make sense? So you have white plus red yields finally what the white one's doing plus finally what the red one is doing. Okay, so with that in mind, this is the law of conservation of momentum. If the momentum lost by one object is gained by another object, then the total amount is constant. There has to be a complete transfer of momentum on here. Obviously, we're going to get more specific. We're going to talk about, well, what if, but extremely general, the ideal conditions. If the momentum lost from one object is gained by another object, then you have witnessed the law of conservation of momentum. Something was conserved. You started with this, you ended with this, but it was initially this, now it's finally that. But the amount of momentum was successfully 100% transferred from A to B. This is also looking at Newton's third law, equal and opposite, right? You bang shoulders with someone in the hallway that's working opposite the direction of you or walking opposite the direction of you. You don't lose your shoulder. They don't lose their shoulder, right? So there's that transfer of energy from there. You can feel those two forces touching each other. There is an extreme misconception right there. The misconception is that the after effect of like, well, you kind of go backwards a little bit and they go backwards a little bit, right? Because of the impact of the shoulders. That would be Newton's first law. Newton's third law is you're walking down the hallway, someone's coming opposite your direction of motion, your shoulders touch, freeze, right there. The force transfer from your shoulder to their shoulder to your shoulder. That would be Newton's third law. The after effects of that would be Newton's first law. So think about football players tackling each other. The moment that they collide with each other, freeze, that's Newton's third law. That's the law of conservation of momentum. So this should make sense. Two objects collide moving at the same velocity. How far back do they move? They both move back in the opposite direction because one momentum was transferred to the other object, right? So if you were moving forward, you're now going to go backward, right? At the same amount, right? Because both of those objects were moving at the same velocity, for instance. Okay, so cool. Newton's third law of motion. Once again, one object working opposite the direction of motion are going to be equal and opposite. So F1 equals negative F2. So this is also going to work for time, right? Because the same amount of time is being applied to this system. So F1 times T1 equals negative quantity F2 T2. So the impulses are equal in magnitude and opposite in direction. So this is where impulse comes into play. So now we can throw Newton's third law and impulse together to get the impulse momentum theorem. M1 V1I equals negative quantity M2 V2I. Breaking that down even further, you would have like M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. Makes sense? So by using your forces knowledge, you can apply that to your impulse momentum theorem to be able to successfully solve for two objects when they, final thing in this unit, collide together. Okay? Alright, so here's another example. Let's talk money, right? You have $100, he has $100. You go out and you spend 50, but Jill has 150 because you gave her 50 bucks. But both of you together at the beginning had $200. Jill gained $50 of Jack's money, but Jack and Jill still have $200. So what was the change here that they had? Jack's change is going to be what? What should be behind this blue screen? Jack's change is going to be negative 50, right? Because he gave up negative $50. What's Jill's going to be? Jill's is going to be, remember guys, you want conservation. So conservation would mean if I lost this much, if I lost $50, how much did I gain? You gained $50. So here's an example of the conservation of money. Not the conservation of momentum, obviously, but it's still showing you how things are conserved. You started with this amount, you ended with this amount. How did you change this? One was given 50, one had 50 taken away. Same amount there, same amount you started with is the same amount you ended with. Okay, here's another example. Fullback and a linebacker collide with each other. One has a momentum of 100 kilograms times meters per second. The other one is 120. One is heading towards the right, the fullback. One is heading towards the left, the linebacker. So what's momentum here? Calculate it real quick. Please don't grab your calculators. You have a positive 100 and you have a negative 120. So your change in momentum, the actual momentum after effect, is going to be, jot it down guys, it's going to be negative 20 kilograms times meters per second, yeah. Final answer, box it. Okay, next, skaters. This is sweet, do this. Like if you can totally do this, do it. Just get two rolly chairs, you don't have to dress all up in your inlines or whatever. Or grab some skateboards or grab some skis in the wintertime, whatever. There's tons of different surfaces that you can do this. Think about your coefficient of friction though, so you'd want the slipperiest, the most slippery surface to successfully run this. Okay, so You have two skaters. You're facing in opposite directions, correct?